Welcome everybody. It's my pleasure to introduce to many of you who already know him, Ferran Vidal PhD. He's been working in the lab here in the aero department since fall 2011, and in the process he got a master's thesis, and now he's going to tell us about his work in simulation methods for plasmonic structures. So the regular format for these defenses is that he'll present. If there are very quick clarification questions you may ask, but otherwise I would ask that you refer your questions to the end when we are going to have time for questions and answers. Okay, so Ferran, the floor is yours.
Thank you, Jaume, for the kind words. Thank you very much, everyone, for coming. Today I'm going to present the work that I've been doing during my PhD, that as Jaume said is simulation methods for plasmonic structures. First of all, let me introduce you a bit what plasmonics is, because it might not be familiar to many of you folks. Plasmonics is an emerging discipline that studies the resonant oscillations of electrons that occur at the metal-dielectric interface. These oscillations are generated by the interaction of electromagnetic waves with metallic nanostructures. One of the most important aspects of plasmonics is the fact that they enable an unprecedented control of light at the nanoscale, thanks to these two really key concepts, which are confinement of light that lead to large field enhancements. And these two concepts are quite important for this talk, so I'm just going to spend the first few slides motivating and illustrating these concepts through this really simple example. The example consists of two infinitely long gold nanowires separated by a close distance or gap, illuminated with a plane wave. At the top here you see a top view of these two nanowires, and the colors correspond to the amplification factor of the incident field. That is, how many times the incident field is enhanced in this gap region. And in the bottom, I'm showing the exact same thing as the gap, as a function of the gap separation integrated along this distance. As you can see, when the separation is quite large, there's nothing much going on. But as soon as we start entering in the nanometric and sub-nanometric regime, we start seeing these large amplifications that just grow and grow drastically up until more than 200 times when the separation is 0.5 nanometers. And again, this all happens at a fixed frequency. So this is just an artifact of the nanowires getting closer together. And this is precisely an illustration of confinement and resonances. So this system is able to trap light in the gap region, which in this case is 1,000 times more than the incident wavelength. And thanks to this extreme confinement, you get these large amplifications or resonances that are tightly localized in this gap region. These resonances are also called electromagnetic hotspots. This was happening at a fixed wavelength, but for the same structure, you can have these resonances at multiple wavelengths. Here I'm showing again the incident map, the enhancement of the incident field as a function of both the distance and the incident wavelength. The resonance in the top was the one I showed in the previous slide, and as you can see, that for shorter wavelengths, you can also excite further resonances in these sub-nanometric distances. Okay, so we have this tight confinement of light and these large resonances. What are they useful for? And this turns out to be one of the most important aspects of plasmonics, the fact that they have a lot of applications in very different disciplines. I'm here just going to name a few of those applications, but just so that you know, there are many more out there. For instance, they can be used as sensors, where, for instance, we want to detect the presence of toxins, chemical agents, diseases, or explosives. And we do that by attaching a metallic nanoparticle, illuminating it with an electromagnetic wave, and measuring the shift in the resonance as the presence of the agent that we want to detect. For instance, in this case, we have these hydrogen nanoparticles, and we see a shift in the resonant frequency. Another application is in cancer imaging and treatment, where we can selectively target, using these plasmon resonances, we can selectively target the malignant cells and attach gold nanoparticles to them. Then we can leverage these large resonances to transform the electromagnetic energy into heat, so that we can destroy the adjacent tissue while leaving the healthy cells untouched. And finally, another application is in energy harvesting, where we use again these resonances to trap and enhance the sun radiation, for instance in this case in this thin metal film, leading to an increase in the photoemission of electrons, which potentially leads to more efficient photovoltaic devices. And again, these are just 3 different applications, but there are many more out there that benefit from plasmonics. So these really interesting applications motivated us to start looking on ways to efficiently simulate these devices. And that's precisely the overarching goal of my research. develop simulation methods to simulate and design realistic three-dimensional plasmonic structures. In terms of governing equations, we're mainly solving Maxwell's equations in their time harmonic form, where E is the electric field, H is the magnetic field, and J is the electric current. And we're going to have to complement that with advanced models to characterize the electron motion at the nanoscale, since, as you'll see later on in the presentation, it's not a trivial task. In terms of simulation, we're using the hybridizable discontinuous Galerkin method to perform the simulations. And this choice stems from the fact that this is a widely applicable method and especially suited for computational electromagnetics, because it possesses several advantages, such as the fact that it's high-order accurate, unstructured, low dissipative and dispersive. It allows for an unambiguous treatment of boundary conditions, among other advantages. Furthermore, we're going to study how to incorporate parametric variability by using reduced order models combined with the HG's method. In terms of applications, in this presentation, I'm mainly going to focus on a realistic structure, which is the periodic annular nanogap on a thin film. That has been present for very different plasmonic applications, and I'm going to be describing it in more detail later on in the presentation. Great. So we want to simulate these plasmonic structures, but what are the main challenges that we face in simulating them? I'm just going to try to name some of the few challenges that we identified. The first one is the fact that we typically have an enormous mismatch in length scales, because we want to squeeze millimeter-long wavelengths into nanometer-wide cavities. So this mismatch typically requires not only simulation methods, but also meshes that are able to deal with this tight confinement and localized phenomena. Another problem that we're facing is that we're solving wave equation, which is a non-coercive operator. Hence, if we want to solve large 3D problems, where for other equations we would use iterative methods, typically here we cannot, because there are no off-the-shelf preconditioners that work good for different cases. Additionally, since it's a wave problem, we need to hire the method that is able to deal with the dispersion errors that are typical in wave equation problems. Quite separately, another challenge of plasmonic simulations is the fact that, for instance, you need to perform simulations that involve optical constants whose value is not precisely known, because they typically come from experiments and are hence subject to measurement errors. In addition, we're simulating structures manufactured at the nanoscale. So it's important to take into account fabrication tolerances that arise due to these extreme manufacturing constraints. And finally, as I briefly hinted in the previous slide, we're going to need additional modeling to fully characterize the electron motion in the metals at the nanoscale, which is going to be quite demanding. Through this presentation, what I'm going to try to do is to address these challenges individually and propose a solution that fulfills these limitations. So this is an outline of the main points that I'm going to be discussing today. First, I'm going to introduce to you the hybridizable discontinuous Galerkin method for a type of metals known as Drude metals. Then I'm going to extend this approach to take into account parametric variability using reduced order modeling. And finally, I'm gonna pursue the simulation of a more advanced characterization of the electron motion at the nanoscale, which is given by this hydrodynamic model for metals. Okay, let me jump right in the ATZ method. This is the most common scenario that we're going to be simulating, where we have a metal described by its permittivity epsilon sub m prime, embedded in a dielectric with permittivity epsilon sub d, illuminated with a plane wave. And what we do is we encode this variation in permittivity in this piecewise constant permittivity epsilon as a function of the space, and we solve Maxwell's equations together with some radiation conditions on this entire computational loop. But it turns out that for the metal, since we have a local relationship between the electric field and the electric current given by Ohm's law, where sigma is the conductivity of the metal, we can lump both the permittivity and the conductivity of the metal into what's called this Drude permittivity. And this is quite an important magnitude that I'm going to be describing in the next slide, but it's essentially putting together the permittivity, the conductivity, that it's going to have this dispersive behavior because it's a function of the frequency. What exactly is this Drude's permittivity? This permittivity stems from the fact of characterizing the electrons as free particles of an ideal gas. Under this assumption, you end up with an expression for this Drude's permittivity that is of this form. Again, it's dispersive because it takes into account the frequency, and it involves two constants, two optical constants, which are the first one, the one in top, is the plasma frequency, which is the frequency above which the metal starts behaving as a dielectron. That is, it starts allowing full electromagnetic propagation through it. The constant in the bottom is the electron collision rate, which is essentially a damping constant, because as you can see, it's attached to the imaginary unit. And it's the one responsible for modeling the losses that we typically see when electromagnetic waves propagate through the metals. And just to stress how important it is to take into account this gamma constant, I'm showing here the frequency versus field enhancement for a plasmonic structure. And we can see that if gamma is 0, that is, this Drude's permittivity is real, we see enormous field enhancements and really sharp resonances, which is clearly unphysical if we compare it to what it's observed experimentally. But as soon as we turn on this damping constant, this gamma to be positive, we see a decay and a broadening of these resonances, which is much more in line of what can be observed in the experiments. So overall, this is the Drude's permittivity, and again, it's going to be important because I'm going to be referring to it on and on during the presentation. This is the applicability of this model. I mean, it's the most widespread approach because it essentially gives accurate results for a broad range of frequencies because it models both the dispersive and the lossy nature of the metals. It's also known as local model because it prescribes a local relationship between the electric field and the electric current, given by Ohm's law. And perhaps the most attractive feature is the fact that if you have a pre-existing Maxwell solver for dielectrics, you can just use this very compact expression and extend it to a solver to deal with both dielectrics and metals. It of course has some disadvantages, the main one being that as soon as you start going to geometries below tens of nanometers, you start getting results that are not only inaccurate, but also unphysical, due to the fact that you neglect the non-local interactions and the quantum phenomena that start to be important at these scales. So it's important to have in mind these limits of applicability of this Drude model. Overall, now we have our Maxwell's equations on a computational domain that combines both a Drude metal and a dielectric. And if we pursue a hybridizable discontinuous Galerkin discretization of this system and domain, we end up with a linear system of this form, where the unknowns are the magnetic field H, the electric field E, and the tangent component of the electric field, which is this E hat. We'll now take a look at a typical HGG mesh, high-order mesh, just to get a little bit more insight on where these variables live. So we have the local variables, the electric and magnetic field, that are defined at the element level. That is, for each degree of freedom in each element, we have 6 components, 3 for the electric field, 3 for the magnetic field. And this E hat, the tangent electric field, lives on the global phases. And for each degree of freedom on each phase, we have 2 components since we use the basis of the tangent vectors to span the solutions. Thanks to this duality between local and global degrees of freedom, this is the HG system. This system turns out to decouple, thanks again to these local and global degrees of freedom, and we can end up with a system like this that has a much reduced number of degrees of freedom, since it only involves the degrees of freedom corresponding to E hat. We go ahead, solve this linear system using, for instance, a direct solver, and then we can recover the local variables, electric and magnetic field, quite efficiently at the element level. And it has been shown that that the variables with this approach converge optimally at the rate p plus 1, where p is the approximation order of the space. Okay, let me now show you, for a realistic problem, how this method performs. This is the periodic annular structure that I was referring to in the beginning, where we have a thin gold film over a silica substrate, where we pattern an array of alumina nanogaps distributed as the symmetries of the square and illuminated from below. This structure is interesting to us because for a fixed gap size, in this case 2 nanometers, it's able to excite resonances for a broad range of frequencies, just by simply tuning the ring diameter and the periodicity. For instance, we're going to be focusing in the low terahertz regime, where this structure was shown in this paper to act as a sensor to detect the presence of thin film materials as thin as 1 nanometer. So for the wavelengths that we're interested in, we have a mismatch between the wavelength and the gap of about 6 orders of magnitude. So you can imagine what are the challenges computationally here. And finally, the figure of merit that I'm going to be discussing is the field enhancement integrated along the gap volume of these rings. Leveraging the symmetries in the system, we can reduce the computational domain to the one you have up here, And then we pursue a higher order discretization of this computational domain, where we have a 3D mesh and a 2D slice. And as you can see, since we expect a tight confinement of the fields near the gold and around the gap, we're going to concentrate the elements of the mesh to really capture the solution in those areas. Perfect. So what I'm showing here is a vertical cross-section of this annular nanogap at 4 different angular values. The angles come if you look at it from the top. The colors correspond to the field enhancement, that is, how many times the amplitude of the incident field is enhanced in this region. And I'm going to show an animation that essentially performs a frequency sweep, and you're going to see how these fields change as soon as we move close and far away from the resonance, which happens at about 0.4 terahertz. As you can see, as soon as we start approaching the resonance, we see a lot more penetration of the incident field in the metal, and this penetration decays as soon as we move away from the resonance. Another important fact here is that the field enhancement is constant along the slit for all the angles, even though it presents larger values for the angles that are close to 0 degrees. And to me, the main takeaway here is the fact that if you look, for instance, at alpha equals 0, at the upper tips of the gaps, you see that we have an enhancement of more than 3 orders of magnitude at the tips, and that it decays quite rapidly within distances of less than 10 nanometers. So in order to capture these really sharp gradients in the solution, it's imperative to use high order methods, because with other types of methods, we would definitely need a lot of discretization elements to fully capture this behavior. So this is, in my opinion, the main takeaway here, and how XDG enables for these simulations. These field enhancements give rise to what's called the extraordinary optical transmission. It turns out that since this structure is illuminated from below, the only way that the light can pass through the structure is if it passes through the gaps, because the metal is completely opaque to the incident field. So here I'm showing the frequency versus transmission, and we see that at the resonant frequency, the maximum transmission that this structure attains is about 0.75% of the incident light. And one might say, okay, this is rather low. But it turns out that this 0.75% of incident light is able to be transmitted only through an area of 0.008% if you compare it in relative terms to the area of the gold. And this is due to this enormous field enhancement and to this extraordinary optical transmission phenomenon for which these structures are specially designed. Okay, let me now talk a bit about reduced to the modeling. First of all, why do we even care to do reduced to the modeling? Truth is that when one wants to do these kind of plasmatic simulations, there are a lot of sources of uncertainty that one encounters. For instance, the alumina that we have been using to fill the gaps, we have been using this thickness-dependent permittivity constant for the alumina. That, as you can see, from very few measurements, you already derive a law, and this is the one you use for the simulations. In terms of gold, here I'm showing in the left the real part, in the right the imaginary part of the group's permittivity. And as you can see, different groups in literature have proposed different results that all come from different measuring techniques. And it's unclear which one is the most suitable to use in the simulations. Finally, due to the extreme manufacturing constraints of these nanoscale geometries, instead of having perfect structures, in this case perfect rings, we're most likely going to have structures that differ quite a bit from their nominal specifications. So it's important to take them also into account in the simulations. Overall, we propose to take into account this variability that comes from both the materials and the geometry using reduced to the model. In this slide, I'm giving a brief overview of what reduced to the model is. We'll assume that all the variability is encoded in this parameter theta, both material properties and geometry. So starting from a high fidelity solver, in our case for the Maxwell's equations with the metals, we discretize it using our favorite finite element method. We end up with a large sparse linear system that hopefully has a fine parametric dependence on theta. If not, there are interpolation techniques quite efficient to recover this affine parametric dependence, which turns out to be quite important if you want to do efficient reduced to the model. We solve for the solution U, and then we evaluate the quantity of interest. For instance, the field enhancement or the transmission that I showed in the previous example. Reduced to the modeling does something slightly different. So if we want to compute solutions at different parameter values, instead of assuming that the solutions at different parameter values are completely independent, we assume that they live on a low-dimensional manifold that is induced by this parametric dependence. If that's the case, then we look for approximate solutions U sub n that live on a subspace of this high-dimensional space. Looking for the solutions of this form, we end up with linear systems that are dense but much more than their high-fidelity counterpart, and they can be typically solved extremely quite efficiently. Once we compute the approximate solution, we can evaluate an approximate quantity. In the next few slides, I'm going to describe how to apply reduced to the modeling for the HDG method for good metals, and I'm going to focus on the case where theta describes geometry variations, which in my opinion is the most interesting one. Okay, so starting from this structure, we have the initial domain, this unit cell, and assume that we have a mapping G that prescribes homogeneous variations of both the radius and the gap. And this is the only variations that I've considered in my dissertation, although it could be extended to more complicated deformations. So homogeneous variations of radius and gap. So for different instantiations of the parameter, we get for instance, two different deformed domains, and then to get the electromagnetic response, we just solve regular Maxwell's equations on these deformed domains. This is one way of prescribing geometry variations, but it turns out to be not the most efficient if you want to then do reduced to the model. And that's why we decided to use a different strategy, which is the reference domain formulation. Instead of solving Maxwell's equations on this deformed domain, we're instead going to solve a transform versions of Maxwell's equations that depend on the parameter on a fixed parameter-independent reference domain. So for each new value of theta, we'll just recompute our equations and solve on the fixed domain. It turns out that these transform Maxwell's equations, that I'm not going to go into too much detail, everything is in the thesis, they most likely are not affine in the parameter theta because they involve complicated interactions between the Jacobians of this deformation map. So what we do is, alongside with doing the HDG discretization for these transform equations, we combine it with an interpolation technique. In our case, we have used the discrete empirical interpolation method in order to recover a linear system that is affine in the parameters theta. And this is what's really going to be the enabler to perform efficient reduced to the model. So again, for each new value of theta, we transform the equations and we solve on a fixed reference domain. To compute the reduced to the model, we rely on proper orthogonal decomposition, where we compute a collection of solutions at m different parameter values. And then we use POD, which is essentially a principal component analysis in which you compute a low-dimensional basis that still is able to maintain the most relevant information of the system. And it's, of course, it has a much lower dimensionality than the initial high-dimensional system. So this is the POD basis, this phi. And then we're going to look for approximate solutions that can be spent as a linear combination of these low-dimensional bases using some coefficients lambda. And these lambda coefficients that depend on each new value of the parameter are what's going to be evaluated for at each new theta. And this approach, together with the discrete interpolation that I showed in the previous slide, are the key ingredients in order to achieve efficient reduced to the modeling for this problem. Okay, now let me show three different examples of three different applications of this framework. First, I'm going to do a parametric analysis. Then I'm going to show how to examine a more complicated structure. And finally, I'm going to try to compare experimental results with simulations and to assess the validity of the simulations. Okay. First of all, a parametric analysis. So we have this structure in the top. And we're going to construct a reduced to the model that encompasses both the frequency and variations on the radius and the gap. That is, we have three parameters. The frequency is important because we want to perform frequency sweeps. And once the reduced to the modeling is computed, there are two main aspects that we need to address. The first one is accuracy. Since we still do not have error bounds for our reduced to the model, we just evaluate this reduced to the model on a test set of random parameters, and we evaluate the relative error in the field enhancement. And as we can see, for the majority of parameters, our relative error is quite low, below 10 to the minus 3, which is generally deemed sufficient for most engineering applications. And another important thing is the computational speed up in evaluating this reduced to the model. So it turns out that for this particular structure, we can compute approximate solutions more than 1,000 times faster than if we were to solve the full 3D HGG simulations. And this aspect is really what's going to be the enabler to perform a parametric variation. So this is just a sample of results where we fix the gap to be 10 nanometers, and then we study the field enhancement as a function of the frequency and the radius. This, as you can imagine, instead of just having a single simulation, you just have now this map of simulations, which allows us, for instance, to track the position of the resonance. And this can be quite interesting from the design perspective. But let me take that one step further. Let's assume that we slice this graphic through the 16 micron line. 16 micron is the nominal value that we have used to construct the reduced basis. And then we end up with this frequency versus field enhancement distribution. This distribution, which corresponds to the radius being 16 microns and the gap being 10 nanometers, we can identify a relevant quantity, which is, for instance, this resonant frequency here, that happens at about 0.55 terahertz. And one question that we could ask is like, okay, what is the sensitivity of this resonant frequency to variations on both the radius and the gap? And this is precisely what I'm showing in this slide. So in the plot on the right, you see as a variation of the radius, the black line corresponds to the resonant frequency when the gap is exactly 10 nanometers, and the subsequent intervals correspond to the sensitivities of this resonant frequency as soon as you move the gap, as soon as you prescribe variations on the gap of 5, 10, and 20%. The main takeaway message from this slide is the fact that thanks to reduce to the modeling, we're able to compute these sensitivities, which, as you can imagine, can be quite useful from the design perspective, since you're able to track the performance of your plasmonic structure when it's subject to variations on the geometry. And the second conclusion is the fact that this would not have been possible without reduce to the modeling, because thanks to these fast computations, we can perform for each value of gap and radius these frequency sweeps to detect the resonant frequency. And as you can imagine, if we were to solve the full 3D HGG system, this would have been much more expensive. Okay. Now let's go to the concentric annular structure, where instead of one ring, now we have 2 rings. And one question that one might ask is, okay, what is the optimal combination of inner and outer radius so as to maximize, for instance, transmission through the structure? And again, to address this problem, we're going to use reduce to the modeling for both the inner and the outer radius and the frequency. So first of all, we need to prescribe an objective function. In our case, we decided to maximize the transmission through a broad range of frequencies, the ones ranging from 0.4 to 0.7 terahertz. And we add this negative term. It's essentially a penalty to penalize designs that lead to a large variation in the response. Since this, we only have 2 design variables, with the reduce to the model, we can evaluate all possible combinations between the inner and the outer radius. And this is exactly what you have up here. So it's the objective function at all possible combinations, where the black lines correspond to the nominal value of the radiuses. And we can identify the combination of inner and outer radius that gives the largest objective function. Using these 2 radiuses, we can compute the frequency versus transmitted power. And as you can see, for the prescribed interval of frequencies, it of course shows more enhanced transmission as opposed to their single ring counterpart, which is essentially what we were looking for. Again, this is a very simple example, because I'm here just exploring 2 different design variables. But this serves to us as motivation to perhaps use this reduced to the modeling framework to explore more complicated structures in which you might have more than 2 parameters, and hence you might have to use, for instance, optimization to find the optimal parameters. Okay. Let me now talk a bit about experiments. So we have, again, this same annular structure for 2 nanometers, and it was reported in this paper in 2015 that there was some mismatch between the experimental data and the HGG simulations with the drill model. Even though these two profiles agree qualitatively, there's, as you can see, a mismatch in the resonant frequency. And this is what motivated us to explore, like, okay, what are the possible causes of this discrepancy? Can we try to nail it down and have a more predictive model? And this is precisely what I'm going to address now. As I briefly mentioned before, there can be multiple sources of uncertainty in this problem. For instance, we're using these thickness-dependent alumina for the gaps, but it turns out that due to different deposition conditions, the effective thickness of the gap might be smaller. So we might be using the wrong value of the permittivity. Also, as far as the gold is concerned, we're using these values that correspond to bulk gold. But here we have a structure that has a thin film of gold. So we anticipate that there might be some discrepancy here. And there's again the question of the imperfect geometry of the rings that we have when we manufacture these structures. All in all, what we decided to do is develop a reduced to the model for these 7 parameters. First of all, the frequency, because we want to perform frequency sweeps. And then we also take into account the geometry of the rings, both the gap size and the radius, modeled as plus minus 5% of their nominal values. And we also take into account variability in the optical constants. And the confidence intervals for these optical constants are the ones given by the experimental measurements in the literature. Once we have computed this reduced to the model, what we can do is, for each new instantiation of these parameters theta, we can compute these frequency versus field enhancement profiles. And obviously, for different values of theta, we're going to have different curves. For instance, the black was the initial one, and I'm showing here a red one and a blue one. And these curves are going to have different shifts with respect to the experimental data. And then if we look at these parameters as if they were random variables, then the shift is also a random variable. And one thing that one might ask is, okay, what is the impact of each individual parameter on this shift? And we decided to study that using global sensitivity analysis. These results correspond to what's called the first order sensitivity index of the parameters. These indices are essentially, so for instance, let's assume that we want to compute the index for the radius. So the index for the radius, what it means is the expected reduction in the variance of the shift if we fix the value of the radius and we let the rest of the parameters vary in their respective intervals. In order to compute these indices efficiently, we combine reduced to the modeling with the quasi-Monte Carlo indices given in this reference. Again, these are the results, and the 2 main conclusions, in my opinion, the first one is the fact that you actually get a hierarchy of importance. We see that both the radius of the ring and the permittivity of the illuminated gap explain almost 75% of the variation that we have of the shift. So one should really put a lot of resources, both computationally and experimentally, to faithfully describe both the radius and the permittivity. Whereas, for instance, the plasma frequency and the permittivity of the silica substrate are virtually irrelevant to explain the shift. So instead of developing a reduced to the model for these variables as well, one should just go ahead, fix them to a certain value, and disregard them altogether. The second conclusion, which was something quite surprising, is the fact that, as you can see, the effect of interaction is almost negligible, which means that the variables are almost independent from each other. And the main consequence of this fact is that, for instance, instead of having computed an enormous reduced to the model with all the parameters at once, which typically involves exploring a multi-dimensional parameter space, and this is not an easy task, we could have instead developed a collection of smaller reduced to the models for each parameter independently, and thus be much more efficient. All in all, if we take the combination of parameters that gives the least shift with respect to the experimental data, again, this need not be the actual combination of parameters, but it's just the one that gives the best fit to the data, we see that even though we are guided towards the right direction, because we decrease the enhancement and the shift takes us closer to the experimental data, we're still not able to fully bridge the gap between the simulations and the experiments. So as as important as it is to take into account this variability, we might be missing some relevant physics of the problem. There might be something that we're not fully capturing here. And this is what's going to be the last part of my talk, trying to enhance the physics of this model. And this is precisely the hydrodynamic model for metals. So the hydrodynamic model for metals is essentially an extension of the Drude model that takes into account the non-local interactions between electrons that starts to become important at geometries below tens of nanometers. These non-local interactions are accounted for using an additional hydrodynamic pressure equation that needs to be solved alongside with Maxwell's equations. Again, this model enlarges the applicability range to up about 0.5 nanometers, which is when quantum effects start to kick in. And again, quantum effects are not included in this model. The main physical difference between both models is in the induced electron density rho, where for the Drude model, this induced electron density is infinitely squashed at the metal-dielectric interface. In the hydrodynamic model, we see that this induced electron density is spread inside the metal. Hence, it essentially diffuses the boundaries of the metal and changes the electromagnetic response. To further illustrate this aspect about the induced electron density, let me show you some results regarding, again, this annular structure, but now without the substrate and without any filling of the gaps. We removed all this just to focus on the effects of the metal and not have any contamination from other sources. And now we show the induced electron density for both the Drude model and the hydrodynamic model. And as you can see, for the Drude model, the induced electron density is a Dirac delta at the interface, which essentially which causes the geometric gap to be equal to the effective gap. And the effective gap is the gap that is seen by the electromagnetic waves as they propagate through the system. And the main consequence of this infinitely squashing is the fact that the penetration of the electromagnetic waves in the metal is very poor for the Drude model. Conversely, for the hydrodynamic model, we see that the induced electron density, instead of being a Dirac delta at the interface, it has a spreaded profile that penetrates inside the metal. And the main consequence is the fact that the geometric gap is enlarged. So the gap that is seen by the incident electromagnetic waves is larger. As a consequence of this enlargement of the gap, we have that, of course, since the waves are now able to propagate through a wider region, we're going to have more transmission just because there's more space for the waves to propagate. But since the gap is larger, we have less confinement. And since we have less confinement, we're going to have a decrease in field enhancement. Here, that's precisely what I'm showing here. I'm showing the ratios between maximum enhancement and maximum transmission for both models. For this structure, where the gap ranges all the way from 0.5 nanometers up until 100 nanometers. And we can identify two different regimes here. For gaps above 10 nanometers, we see that the electromagnetic response for both models is virtually the same. So this means that if you're interested in computing simulations above around 10 nanometers, then you should not bother solving the more complicated hydrodynamic model because you might actually get the same results as if you were solving the simpler Drude model. But as soon as you start going to geometries below tens of nanometers, the hydrodynamic model starts giving solutions that are quite different from the ones in the Drude model. And if we go all the way to sub-nanometric scales, we can have, for instance, an increase in transmission of more than 20%. So this is to stress how important it is to take into account this advanced physics if we're solving in this domain of interest. Mathematically, in addition to the Maxwell's equations, we need to solve inside the metal these two additional equations, where J is the electric current and rho is the induced electron density. And this beta parameter is the only one I have not taught so far. If this beta is known as quantum parameter. If you set it to 0, then you recover a local relationship between the electric current and the electric field. And this local relationship is nothing but the Drude model that I've been describing on and on up until now. Conversely, if this beta is set to a non-zero value, and this is usually the value that is given in literature, where Bf is the Fermi velocity of the ball, which is nothing but an optical constant, then as you can see, we have a non-local relationship between the electric field and the electric current. And in order to get the full electromagnetic response, we need to solve this coupled system of equations altogether. And we're going to use the hybridizable discontinuous Gorky method to solve these augmented equations. So now we're left with a multi-physics problem in which we solve for Maxwell's equations in the dielectric and for these augmented Maxwell's equations in the metal. In terms of addition of boundary conditions, we need to prescribe that the electric current is tangential at the metal interface, and physically this means that the electrons cannot escape the metal, that the electrons are confined within the metallic volume. In terms of degrees of freedom, as you can imagine, now we're going to have a lot more degrees of freedom. For the global variables, in addition to the two components of the tangent electric field E hat, now we have an extra component, this rho hat, which are the traces of the induced electron density on the global faces. And as you can imagine, since we go from 2 components in the dielectric to 3 components in the metal, these simulations are going to be more expensive. And in terms of local variables, now we have 10 components, 3 for the electric, 3 for the magnetic, 3 for the electric current, and 1 for the induced electric density. If we now pursue an HGG discretization, we end up with this larger linear system, but again, thanks to the decoupling between local and global degrees of freedom, we can reduce this system to the one that only involves the E hat and the rho hat degrees of freedom. This is the system that we solve using a direct method, for instance, and once we have this E hat and rho hat defined on the global phases, we can recover the local variables at the element level very efficiently. And again, we showed in the thesis that all the variables converge optimally at the rate p plus 1, where p is the approximation order of a space. Okay, so now revisiting this problem, this periodic annular nanostructure, where we were observing this mismatch, since the nanogap is of 2 nanometers, we might expect that the non-local interactions actually play an important role in this problem. And it turns out that they do. So first of all, we examine the optical transmission of this structure, and as you can see, where before we had a maximum transmission of about 0.75%, now we get a 21% in transmission to boost it all the way to 0.9% of incident light. And again, just as a reminder, the 0.9% of incident light is being transmitted through an open gap area of 0.008%, which gives us more than 2 orders of magnitude in terms of extraordinary optical transmission. Finally, if we compare it to the experiment to the field enhancement for which we have experimental data, we see that for the exact same parameters that we use to compute the black solution, we see that we have a shift in the resonance that guides us to the closer to the experimental data and a decay in field enhancement. But again, by considering this more advanced model for the electron motion, we're still not able to fully bridge the gap between the simulations and the data. And the main conclusion here is, first of all, the fact that before we were certainly not capturing the physics. We were missing something in our previous model. And this something is these non-local interactions that are fully captured by the hydrodynamic model for metals. And secondly, that it would be extremely interesting, although it has not been done here, to fuse these 2 approaches. That is, to extend the reduced to the modeling framework to the hydrodynamic model for metals, in order to have a much more predictive tool to essentially guide the simulation and design of plasmonic structures. Okay, let me now conclude. These are, in my opinion, the main 2 contributions of my work. The first one is the ability to simulate realistic 3-dimensional plasmonic structures using the hybridizable discontinuous Galoppen method for metals described with both the Drude model and the hydrodynamic model. And we have used it to this realistic 3D periodic annular nanogap that had not been addressed before due to the multiple simulation challenges that we've seen over and over. And secondly, this reduced to the modeling framework that enables you to carry out, for instance, parametric studies. And the importance of these parametric studies can be, for instance, to derive sensitivities of the performance of the structure with respect to geometry variations. That can lead to to gain a lot more insight on the performance of the structure, and potentially to guide the design towards more complicated plasmonic structures. And again, in my opinion, these are the 2 most important contributions of this work. Looking forward, there are a lot of future lines of research that could be investigated. First of all, the use of iterative solvers for 3D problems, because for the hydrodynamic model for metals using direct solutions, we were already, it was already quite expensive to get solutions for these more complex structures. So if we want to work on larger problems, we might actually have to start looking into preconditioners and iterative methods. In terms of enhanced physics, we would really like to incorporate quantum effects to go into the nanometric and subnanometric scales. And this is just a cartoon of what these effects look like. So when you're in these geometries, the electrons start tunneling out of these metal nanoparticles, and you have this flow of electrons that is in between these nanoparticles. So now The boundaries between metal and dielectric are not so strict, since now you have to solve for this flow of electrons in a region surrounding the system. And as you can imagine, this can be quite computationally demanding and also difficult from the modeling perspective. In terms of reduced to the modeling, we definitely need to incorporate error bounds to certify the accuracy of the solutions. And we would like, as I've already mentioned, to extend the reduced to the model to this more advanced physics described by the hydrodynamic model for metals, in order to have a much more predictive simulation method. In terms of applications, there are a lot of things that could potentially benefit from this research. The first one is that we would really like to use this reduced to the model to investigate more complicated structures. And here's just a sample structure of this annular nanogap surrounded by concentric grooves. And as you can imagine here, there are a lot of geometric parameters whose value is not known. For instance, the depth of the grooves, the pitch, the radius of the gap, the width of the gap. And it's unclear if you want, for instance, to enhance the transmission properties of this structure, what is the optimal combination of parameters. So using reduced to the model alongside with optimization techniques might be a good strategy to address these problems. Looking a bit forward, we would really like to take a look into incorporating 2D materials to plasmonic structures. This has already been quite studied from the experimental standpoint, and the 2D materials such as graphene or black phosphorus have shown to enhance the properties of plasmonic structures, basically by decreasing the tremendous losses that we see in metals. But from the computational perspective, as you can imagine, this is quite challenging because it essentially forces you to simulate one atom thin layers that potentially have anisotropic behavior. So it just adds an extra layer of complexity into the simulation. And finally, if we extend it to these quantum scales, it would be quite interesting to take a look at the quantum devices such as plasmonic lasers or plasmonic circuits that have attracted the interest of the community in the recent years. And we would strongly think that they would benefit a lot from the advanced simulation methods that we propose. Okay, finished. Let me now take some moments to enjoy and acknowledge all the people that have made possible me being here. First of all, Jaume, for believing in me, for giving me the amazing opportunity to come to MIT. Without his mentorship and guidance, this PhD would not have been possible, so thank you very much. Also to my other advisor, Dr. Keng Nguyen, for his continuous support and assistance throughout the years, and for being there to solve all the little problems and not so little problems that have been appearing throughout the years, and believe me, there have been plenty of problems. Also to my other committee members, Professor Yusuf Marzouk and Professor Tony Patera, for his continuous support, guidance, feedback through the multiple meetings that we've had through these years. Your continued interest in my work has really motivated me to keep forward. So I would really like to acknowledge your help. Also to my readers, Professor Sanyun, which is not here today, for showing us these really cool applications, for hosting us in Minnesota, and for also being very useful for the development of this thesis. And finally, to Professor Nicholas Fang for agreeing to be a reader, taking his time to improve the final quality of the thesis. So thank you very much. Also to the funding, the AFOSR, and La Caixa, which were the ones that in the first place made it possible for me to come here with a fellowship 6 years ago. So again, I'm deeply grateful to this program. And finally, funny part, my Boston family. So to avoid missing somebody, I just decided to dump all the pictures here, and you guys just find yourselves. It's been truly great. I mean, without you, this would not have been as much as funny as it has been. Both my roommates, my lab mates, and Spanish and Catalan people that I've had the fortune to meet throughout my time here. And if I had to highlight some of the points, for instance, the travels, watching Barcelona games, that as you can imagine, it's something that I deeply like to do. And also I would like to acknowledge the Spain at MIT football team for establishing a dynasty and winning multiple football competitions throughout these years. So to all of you, thank you very much for making this possible. And finally, to my Catalan family, all my childhood friends that made it really difficult for me to live It's really difficult for me to leave when I was there, and now make it quite easy to come back because they always welcome me. To all the people that have contributed to my joy while I was here, Messi, all my childhood friends, and of course my family, my cousins, grandparents, uncles, and finally my mom, my dad, and my brother. This would not have been possible without you, so thank you very much. And with that, I conclude. Thank you very much for your presence here.
Well, I'm glad to see that you consider Lionel Messi part of your extended family. I'm sure
It's important.
I'm sure he would appreciate that later. But without further comment, I'd like to ask questions, invite questions from the audience at this point.
I have a plot with HPV group versus Ferran data. Have you got any other, like, are there any other results you can talk about, like other simulations, or is the HPV group what the normal case?
I would say that for these regimes, it's probably the one that is the most accurate. Yeah, one thing that could be included is, for instance, comparison with commercial software, such as the ones with FDTD or console. But it turns out that for these complicated structures, it's really complex to get solutions from commercial softwares, just due to the fact that there's an enormous mismatch of length scales here. Because the gaps are in the nanometric scale, and the radial of the rings is on the micron scale. So, in order to get solutions, for instance, with a finite difference scheme, I have not tried it, but during our interactions with Professor Sanyun, they told us that they could not perform those computations using commercial software. So that's one of the main points of the HG simulations, just enabling us to get a response that is sort of accurate for these problems.
Other questions? Okay. There are no other questions. What I would like to do is I would like to ask everybody except the faculty to leave the room and leave it with the candidates. You can wait.
Turillo nunca más.
No sabrás.
Oh.